In this video we're going to look at the rate determining step. So first of all, most chemical reactions don't actually occur as a single step. They're actually in multiple stages. And each one of those stages will occur at a different rate. Some will be fast, some will be slow. So if we consider the fact that when a reaction occurs, the reactant particles are colliding and they have to collide with enough energy in order to react, if you have more than two reactant particles, then the likelihood of, let's say we had three reactant particles, the likelihood of all three of them colliding at the same time with the correct activation energy is very, very unlikely. So most reactions actually do occur as multiple steps. And again, from the organic side of the course, you will have been quite familiar with multi-step mechanisms, reaction mechanisms that create intermediates. So we're going to be dealing with reactions that create intermediate products, which are then used up in a later step of the reaction. Now, what's important to take from this is that obviously the overall reaction is, the equation is still correct. You still have that amount of reactant, and you get those amounts of products. Okay, so our multiple step reactions, if they are creating any intermediates, those intermediates must be used up before the final step. So that overall, if you combine the entire left hand side of all of your steps and the entire right hand side of all of your steps, you will end up with the same stoichiometry as the overall reaction equation. So when we actually measure the rate of reaction, we're limited by the slowest step. So if it's a 4-step reaction, we're really only measuring the slowest of those 4 steps. And the rate equation represents that. So of the slowest step, we call that the rate determining step. So if I had a reaction here, 3 steps to that reaction, the first one was fast, the second one was slow, and the third one was fast again, then the rate determining step is step 2. The slowest step is your rate determining step, and that is what the rate equation is dependent upon. So we can use the rate equation to identify a few things. Number one, we can see straight away, as long as we have the balanced overall equation and the rate equation, we can say whether it is or isn't a multi-step reaction straight away. The other thing we can do is if we know the steps or we know the mechanism stages, we can use the rate equation to identify which one is the slowest step and therefore the rate determining step. And we can also use the rate equation to actually construct possible mechanisms and possible steps to a reaction. So we have an example here. So here is a reaction, 2A plus B makes 2C and D. And here is our rate equation. Now, when we spoke about the rate equation before, we said that it was the concentration of the reactants raised to the power of their order. So A is first order, B is second order. That is still true. But it also tells us something else. The fact that A is raised to the power 1 tells you that one molecule or one particle of A is used in the slowest step, in the rate determining step. The fact that B is to the power 2, it's still second order, but it also tells us that there are 2 molecules or 2 particles of B in the rate determining step. So let's have a look at our 2 possible steps. So here we've got A plus 2B reacting to form C plus D plus E. And then in the second step, another particle of A reacts with the E that was formed here to produce another particle of C and reform a particle of B. So in order to identify the rate determining step, all we need to do is look at the stoichiometry of the rate equation. So A to the 1, B to the 2. So which one of these steps has 1 particle of A, 2 particles of B? It's step 1. So this is our rate determining step. Now, these are the 2 proposed steps. And notice how there's an E involved, but there's no E up in the overall equation. Now, if we combine the left hand side of both steps, we will end up with 2a plus 2b plus e. And if we combine the right hand side of both steps, we end up with 2c plus d plus b plus e. And then cancel anything that appears on both sides. So the e is on both sides, so that cancels. One of the b's cancels. And that leaves us with 2a, 1b goes to 2c and 1d, which, if we look back, matches our overall equation from the very beginning. So look at this example then. So the overall reaction is x plus 3y goes to xy3. And the rate equation shows that the reactant x is first order and the reactant y is second order. But it also tells us that in the rate determining step there is one particle of x, two particles of y. Which one of these steps matches that? It's step 1. So this must be our rate determining step. And again, if we look at the overall, so if we combine all of the left hand side, we have x plus 3y, because there's a 1 on the bottom as well, so 3y plus xy2, and on the right hand side we have xy2 and xy3, and the xy2 appears on both sides, so it cancels, leaving us with x plus 3y goes to xy3, which again matches the original equation that we had. So we can use the rate equation to identify if which one of our steps is the rate determining step. The other thing we can look at is we can use the rate equation to determine whether a reaction is going to be multi-step or not. Very quickly, you just look at the stoichiometry of the rate equation, x to the power 1, so that tells you need one particle of x, and y to the power 2, which means you need two particles of y. How many x do we have in the overall? 1. How many y's do we have in the overall? 3, not 2. The stoichiometry does not match. This must be a multi-step reaction. Go back to the first one. The stoichiometry of the rate equation tells us we need one particle of A and two particles of B. Does that match the stoichiometry of the overall equation? No. It says 2A, whereas this is A to the 1, and it's just 1B, and this is B to the 2. So the stoichiometry of the overall reaction do not match the rate equation, so again, this must be a multi-step reaction. The other thing that we can do is we can propose our own multi-step reactions using the rate equation. So here we have a reaction, 2NO plus H2 goes to N2O and H2O, and the rate equation is here. So straight away, when we are constructing multi-step reactions, what you should always start with is you'd only ever be asked to do this in 2 steps. So we've got step 1 and step 2. Okay, you're never going to be asked to propose more steps than that. So for step 1, I always make step 1 the slowest step. And you know the reactants for the slowest step because of the rate equation. The rate equation tells us that in the slowest step you have 2 particles of NO. Are going to form something. Okay. Now step 2, because we're only doing 2 steps, we know that by the end of step 2 we must have the products that have been told to us in the overall reaction. So using the rate equation you can get the first half of the first step, and using the products from the overall equation you can get the second half of the second step. So we know, because of the rate equation, we must have 2 molecules of NO in our slowest step. And because of the overall equation, we know that by the end we must have N2O and H2O. So what goes here doesn't really matter. You don't need to be familiar with this reaction or familiar with this equation. just propose something. What do you think? If I had two molecules of NO and they reacted together, what could they possibly form? I'm just going to go with N2O2. I'm going to keep it simple. You could have potentially said that it's going to form nitrogen and oxygen. You're not wrong. Whatever you put here is just a proposition. Okay, it doesn't matter if it's right or wrong. You don't need to be familiar with the actual mechanism. Now, what's going to go here? You've got to make sure that you've used up all of the same reactants as you had in the original equation. So we've got 2NO, which we've already used, but we've got a hydrogen that we haven't used, so that needs to be used up in this step. And you have to make sure that you've used up any intermediates that aren't going to be final products. So our final products are N2O and H2O. So there's our final products. Our N2O2, or whatever you've put here, is an intermediate that needs to be used up. So we're going to put that here. And we've now proposed a mechanism for this reaction. And finally, looking at this one here, looking at this rate equation, it's saying that we need one particle of PCl3 and one particle or one molecule of chlorine. And you could write it out. So we're going to say step 1. We're going to have one PCl3 and one Cl2. And actually, we don't need more than one step. This is a single step reaction. And we can see that straight away because we have one PCl3 and one Cl2, and that matches the stoichiometry of the overall equation. So this reaction is actually a single step reaction. So using the rate equation, you can immediately identify if a reaction is multi-step or single step just by matching the stoichiometry of the rate equation to the stoichiometry of the overall equation. If it matches, then it's single step. If it doesn't match, then it's multi-step. You can identify the rate determining step, the slowest step of a reaction, if you've been given the mechanism and the steps, by matching the rate equation, the stoichiometry of the rate equation, to whichever step has the correct number and proportion of those reactants that appear in the rate equation. And also you can propose potential mechanisms, potential multi-step mechanisms using the rate equation and the overall equation. You need both in order to do this, but that would obviously be provided for you.